In this video, we are going to go ahead and talk about convexity and concavity. Now, this is going to be a basic video where we are going to go ahead and talk about convexity and concavity. However, as we deep dive in the course of mathematics, you will see that I'm going to go ahead and talk about these things in a little more detail. This topic is also going to act very important when we are going to talk about microeconomics. Why? Because I am going to talk there about the indifference curves. I'm going to go ahead and talk about the isoquants. And there, the property of convexity is going to come of very importance to us. And that is because it will help us in the maximization problem. So we will try and understand what happens when the indifference curves are not convex and in fact concave. And we will try and see if they satisfy the property of being convex or not. So the topic of convexity and concavity is also going to be important from microeconomics point of view. All right, so now let's try and understand mathematically what is convexity and concavity. I will take a function y, and let's say y is a function of x, a basic function that I'm taking. Now, a function is said to be concave if when I double differentiate the function, it is less than or equal to 0. A function is said to be convex if when I double differentiate the function, it is greater than or equal to 0. Here, in its more strict sense, a function is called strictly concave when f dash x is less than 0. And it is called strictly convex when f double dash x, okay? F double dash x is greater than 0. Now let's take few examples from it and then we'll go ahead. So let me take a function as x square. What is f dash x? F dash x is 2x. What is f double dash x? F double dash x is 2. 2 is greater than 0, so this function is strictly convex. Let's take another function. F of x is equal to minus 4x square. I'm taking different examples right here. So f dash x will be minus 8x and f double dash x would be minus 8. Minus 8 is less than 0, so this function is strictly concave. Let's take a few more examples. So f of x is equal to ln x. F dash x will be 1 by x. F double dash x will be minus 1 by x square. We know this function is going to have two parts. A, it is not defined at x is equal to 0. Obviously, if x is 0, it gives me infinite minus infinity, it's not defined. For all other values, for x belonging to minus infinity to infinity, except 0, I don't want to take 0 in it, except 0, I'm taking all other values of x. if I take any value of x from minus infinity to infinity, whatever I put, I know that x square will be greater than 0, right? Whether I put x to be minus 4, x square will be 16. Whether I put x to be 4, x square would be 16. So I know that if I leave the negative part aside, this x square, that's the denominator, will be always positive. Numerator is 1. This is also positive. So this fraction is always positive. Multiplied by a negative sign. So this is negative into positive is negative. So this becomes negative. So I know that for any at x equal to 0, my function is not defined. But for any other value, I know that f double dash x is negative. So I know that my function is concave. Right? So let's take one last example maybe. So f of x is given as, let's say, x to the power 4. F dash x would be 4x cube. F double dash x will be 12x square. X square is always positive. So 12x square is always positive. Since f double dash x is greater than 0, greater than or equal to 0 for x, anything, right? For all x's, whether I take x anything between minus infinity to infinity, it's a convex function. If I ask you what happens at x is equal to 0, then at x is equal to 0, this is actually 0, right? Right? So if it is actually 0, so this is greater than or equal to 0. Other than x is equal to 0, at all other values, it is strictly convex, right? But at x is equal to 0, it is convex. All right. Now there is another graphical way to show whether the function is concave or convex. So a function is concave if every line segment joining 2 points on its graph is never, please read this carefully, above the graph. Let me explain you what this means. So I'm saying that, I'm going to go ahead and draw a graph. So I go ahead and draw a graph, something like this. Then this statement says that if you take any 2 points on the graph, I take point A and I take point B. When you take points, any 2 points on the graph and you join those points, right? So whenever you take any 2 points on the graph and you join those points, if that line segment that you have got, this is the line segment that I've got, if that line segment is never above the graph, see, it is below the graph, right? Then it is concave. You can take the 2 points to be as close as you want them to be. So I could have taken the points to be this. But even this line is never above the graph. It's below the graph. So it is concave. Let's take another example. So supposedly, the line that I have is this. The graph that I have, is this. X, O, Y. And now the graph that I have is this. I'm just taking different examples. Okay. Now I take 2 points, point A and point B, and I join these 2 points. Then the line is above the graph, right? It's not below the graph, it is above the graph. So because this line is above the graph, and we said that the line should never be above the graph, I can say that this is not concave. Because the definition of concave is that whenever you join 2 points on the graph, it is never above the graph. But somebody may say that, I'm going to take point C and point D, and I'm going to go ahead and join these 2 points. And this line right here is never above the graph. Somebody may say that this is actually concave, and I proved that this is concave. Well, such graphs in which sometimes you're able to draw a line which is not above the graph, but not always, are locally concave, but not globally concave. Locally, they're concave. In some region, they're concave, which is this region. Because this region actually represents this part. But globally, they are not concave. Throughout the graph, they are not concave. Let's take yet another example. X, O, Y. And the graph is this. Something like this. Now, if I take these 2 points, A and B, and I join them, the line is never above the graph. If I take these 2 points, C and D, and join them, the line is never above the graph. If I take these 2 points and join them, the line is never above the graph. So, it's satisfying concave. But supposedly, I take these 2 points, E and F, and I join them. Then these 2 points are on the graph. But they're also not above the graph, right? But they're on the graph. So such diagram in which some lines are never above the graph, but some lines are on the graph, that is called a concave function. And this, where this is never above the graph. All the lines are below the graph in a way. Something which is something like this. The closest point are never above the graph. This is strictly concave. So this is strictly concave. This is concave, but not strictly concave. This is concave, but locally concave, not globally concave. Now, what we can do is we can go ahead and have a similar definition for a convex function. So let's write that down. A convex function is one in which every line segment joining 2 points is never below the graph. It should never be below the graph. Let's have a diagram for that. So I go ahead, I make this graph. This is X, O, Y. I have to join 2 points and see the line. And the line that I have got is never below the graph. So this becomes a convex function. Okay, let's see another example. So supposedly, my diagram looks something like this. If I take 2 points like these, and I join these 2 points, then this line is never below the graph. But if I take these 2 points and I join them, they are on the graph, but they're never again below the graph. So this is a convex curve. But this was a strictly convex function. And this is just convex function. Now, let's take a few more diagrams. So supposedly, my diagram is this. Now, I take 2 points. I join to those 2 points. These points are never above the graph. So they are, this part is concave. I take 2 points. I join these 2 points. This line is never below the graph. So this part is convex. So this part, is convex. So this part is concave. This will be very important, okay, when I do the cost functions in microeconomics. So for example, if I make my total cost function, something like this. This is my total variable cost. And I have a point of inflection where the slope changes. And I ask you, where is it convex and where is it concave? You do a simple thing. So you take 2 points. You join these 2 points. These 2 points are never above the graph. So this is concave. You take 2 points. You join these 2 points. These 2 points are never below the graph. They're always above the graph. They're never below the graph. So this part is convex. So initially you have a concave function. Then you have a convex function for the total variable cost. Okay. Now, as an assignment, try and make different diagrams for the following. You've done all those, but just try them. Something which is strictly concave. Draw a diagram for something which is strictly convex. Draw a diagram for something which is concave, but globally. Convex, but globally. Concave, locally, may not be concave globally. Convex locally, may not be convex globally. Okay. At last, let's talk about a line. Supposedly what you're given is actually a line. Supposedly this. Now, you take 2 points. It is on the graph, neither below the graph nor above the graph. So this is both concave and convex. A line is both concave and convex. Why? We can prove this simply. Supposedly, what's the equation of a line? Maybe my line is y is equal to 4 times x. So when x takes the value 1, when x takes 0, y is also 0. Right? When x is 1, y is 4. When x is 2, y is 8. And so on. So, my line is something like this. Now, I take 2 points and they don't lie below the graph. They don't lie above the graph. But what do? I find out f dash x. F dash x will be 4. I find out f double dash x. F double dash x will be 0. What's the definition of concave? Concave is f double dash x less than or equal to 0. Or equal to, right? What's the definition of convex? F double dash x greater than or equal to 0. So this has its double differentiation equal to 0 coming up. This has its double differentiation equal to 0 coming up. So this is equal to 0, right? So this is, a line is both concave and convex. But neither strictly concave nor strictly convex. It's just concave and convex. Okay, thank you.